At the end of the last Apollo 15 moonwalk, Commander David Scott performed a live demonstration for the television cameras. He held out a geologic hammer and a feather and dropped them at the same time.
Because they were essentially in a vacuum, there was no air resistance, and the hammer and the feather fell at about the same rate, just as Galileo had concluded hundreds of years before. All objects released at the same time fall at the same rate, regardless of mass, in a vacuum. Today on Little Experiments, we're going to test this hypothesis right here on Earth, using a vacuum chamber and some various objects of different masses.
Here's our experimental setup. We will suspend our objects at the top of the vacuum chamber using magnets. When we pull the source magnets away quickly, the objects in the chamber will fall. We will test 3 objects: a paperclip with bubble wrap attached like a parachute, a metal washer, and a stack of magnets. The vacuum chamber works by pumping air out of the chamber until there is nearly no air left. It can't quite reach a perfect vacuum, but it can get fairly close. You can see the pressure gauge working when the pump is on. The candles need oxygen in the air to sustain combustion. Removing the air removes the oxygen therein, and the flame extinguishes. We are testing whether weight has any bearing on fall speed in a vacuum. Our paperclip parachute is conveniently 1 gram. Our washer is 6 grams, and our magnets are 51 grams. Therefore, the weight of the washer is 6 times more, and the weight of the magnets is 51 times more than the paperclip parachute. When the chamber is full of air, the parachute creates drag and lift in myriad ways as the paperclip falls to the bottom. If this were a high-fidelity scientific experiment, we would use computational fluid dynamics to model out this behavior. Instead, we will make a first-order approximation with a much simpler model of the process, where we only consider one dimension instead of all 3. Here is the free body diagram in the y or up-down dimension, and here is the equation we will use to model our process. The down force is the weight of the object, and the up force is a combined drag and lift force. We can approximate this combined up force using a combined drag-lift coefficient, which is a non-dimensionalized parameter presented in most introductory fluid mechanics books. When we substitute this equation into our equation of motion, we arrive at our final equation. Here is a look at our 2 theoretical equations and the observed data for fall times with air. It's pretty cool that our approximate equation models the paperclip parachute fairly well. When the heavier objects fall, there is very little difference between the air and no air cases. Here we see a side-by-side race between the paperclip parachute and the magnet. Here is our initial data where the chamber has a normal amount of air present. The paperclip parachute takes twice as long to fall to the bottom than does the heavier washer and magnets, just as you would expect. The transparent bands showed the range of minimum to maximum time across the experiments. Alright, it's time to suck out the air and see what the fall looks like in a near vacuum, just like the NASA experiment in space. The spinning paperclip parachute is an added bonus as air rushes through the nozzle behind it. Keep an eye on the pressure gauge as we start at atmospheric pressure, or 0 inches of mercury gauge, to minus 27 inches of mercury gauge.
Alright, this is the moment we've been waiting for. The paperclip parachute versus the magnet in a near vacuum. And remember, the magnet weighs 50 times more than the paperclip parachute.
Here's our data in near vacuum, where we repeated the experiments for each object 4 additional times, just like the initial experiments. As can be seen, the paperclip parachute has changed drastically and is now aligned with the washer and magnets. We see that in the experiments without air, up to experimental uncertainty, the paperclip parachute has the same fall time as the washer and magnet. So what has changed in our equation that accounts for this drastic change in behavior of the paperclip parachute? Well, as we near full vacuum, the air density in the chamber is decreasing to a number near 0. For our approximation, we'll set that to 0, which knocks out our drag lift term, and we recover the typical equation for an object falling on Earth, where the only force acting on the body is gravity. And recall from a previous video, we saw how to measure this little g value. The data shows experiments without air that the paperclip parachute has the same fall time as the washer and magnet, even though the washer is 6 times heavier and the magnet is 51 times heavier.
And therefore, we conclude, just as Galileo did hundreds of years ago, that in a vacuum, 2 different objects fall at the same speed, regardless of their mass or weight, as demonstrated here on little experiments. We'll see you next time.